this. I have too many things open. There we go. That's what I wanted. Okay. Alright, so we're good on that. Let's connect this. Alright. Well, while we wait, see if anybody comes. You could always run through some math problems. Oh, wow. Looks like I didn't do any of these yet. Okay. Whoa. That was cool. I'm gonna do that again. Look how it goes purple. Why is that? Is that just because of my hat? No. It's probably because of my shirt. That's crazy. That's awesome. Okay. Um, yeah, we did want to do that. And then go to the YouTube. Oh, look, there we are. Your channel. I have some videos in here that I've recorded but haven't fixed up yet. Where's the zoom window? Oh gosh. Okay. Yeah. So, what are these videos? Are these all Algebra 2? Yeah, I think they are. That's 1, 2, 3, 4, 5, 6. That's these I've done, right? 1, 2, 3, 4. Some of them look like repeats. The first one is actually trash, looks like. Yeah. Okay, so we'll just start with the calc. We'll just do some calc problems until people get here. Okay. You like the hat? Check out the hat logo. That's pretty nice, right? That's pretty nice. Okay. So let's do this one. I do think I screenshotted him already. So I'm not going to screenshot him. We'll just do him. Okay. Alright, so let's go back to here. Okay. I'm probably not going to break 1,000 rating. I hate to break it to you. At least not for a long time. Alright. So let's see how this is going to go. Okay. I need to get the zoom up again so I can see if anybody actually comes. Okay. What's up, tournament? It's Mathlab time. What's up, Ather? We're not chessing right now. We're doing math. Okay. So how do we do these limits? Well, look how we're doing a left side limit and a right side limit. So we'd plug in if we could, but obviously we can't plug in 1 because we get undefined. So what we're going to do is we're going to think about plugging in values just less than 1 for the first one. Because see how it's that negative means we're doing it from the left side. So we're going to think about plugging in numbers just less than 1. So like 0.99. And we're not necessarily going to do it. We're just going to think about what happens. So what happens if we plug in like 0.99? Well, on the top, what is going to happen? So we plug in the 0.99. What do we get on the bottom? That's what we really want, because we plug in the 0.99 on the top, and we just get some number. But then what happens on the bottom? On the bottom, it's 0.99 minus 1. So that's like negative, really small number. Like negative 0. That's kind of what we do here. So we're doing a number divided by a negative, really small number. So that should be negative infinity. Because remember, a number divided by a small number, if you've got like, a number divided by a small number, that's always going to be infinity. So if it's a number divided by a negative small number, that's negative infinity. So that's the answer to this one. This is going to be negative infinity. But then what about the other one? A number just bigger than 1? So like if we plug in 0.01, well, then we get some number divided by positive, really small number. Positive basically 0. And so if we do a number divided by a really small number, well, then that's positive infinity. And so that's the answer to that limit. So notice that we didn't really plug in those numbers. We just thought about plugging in those numbers. And that showed us whether we needed like a positive infinity or a negative infinity. Are you right? Shouldn't it be positive with the negative up top? Well, it's the same thing, right? Shouldn't it be positive with the negative up top? I mean, if the negative's on the top or bottom of the fraction, that's fine. Can I pay you to do my business analytics class? Yeah, honestly, probably. I don't know if I know the answers, but you can definitely pay me and I'll do my best. Math is greater than chess. That I agree with. That I definitely agree with. Okay, so what is this? This is just showing different properties because the limit as x approaches 0 of 1 is 1. Then the limit as x approaches 0 of 1 over x squared equals infinity. Oh, and that. You can do that. Okay, so they're just showing how if you combine a number with infinity, it's still infinity. And there, if you do 2 divided by infinity, you get 0. And there, if you do 3 times infinity, it's still infinity. That's all they're showing there. Both, I got it wrong? Well, tell me louder if I get it wrong, my guy. No, I guess it should be negative on top, yeah. Oh, I guess that does matter. Yeah, if I get something wrong, tell me louder. When are we going to get into partial differentials or non-homogeneous differentials equations? No, we're not going to do that. Okay, well, so since I got that wrong, so you do just get a number, but it should be a negative number. Yeah, that makes sense, because when you plug in 1, you basically get a negative number. Okay, yeah. So I guess we're going to do it again. All right. I appreciate for calling me out when I was wrong. Very useful. All right, let's do it again. So how do we solve these limits? Well, see, it's the same function. We just got the one on the left side and the one from the right side. So let's start with the one on the left side. So what do they even mean by the left side? They mean plug in a number just smaller than 1, just less than 1. So let's think about doing that. What if we plug in like something like 0.99? So basically 1, just a little bit less than 1. And let's kind of plug it in and see what happens. So we got basically 1 squared minus 3 times basically 1 over basically 1 but a little less minus 1. So let's think about what we have here. We've got, what is it on the top? Well, the top, 0.9 squared, so basically 1 squared is basically 1, minus 3 times basically 1, so that's sort of just like minus 3, over basically 1 minus 1, but a little less, so sort of like negative 0. So remember, all of this is just like in terms of basically, but that's kind of how it works at infinity. So what do we have then? We have basically negative 2 over negative basically 0. So, well, the negative divided by negative, those are just going to cancel out. And 2 divided by a really small number, so that's going to be positive infinity. So as it approaches 1 from the left, it'll be positive infinity. And then, since this is a single root asymptote, just x to the first, we expect this to be opposite on the other one. But let's plug in and see. So here we're going to plug in a number just bigger than 1. So basically 1, but a little bit bigger than 1. And what's going to happen there? So we have, I mean, the same thing on the top, actually. Basically 1 squared minus 3 times basically 1 over basically 1 minus 1. So we get the same thing on the top. We're basically getting negative 2 on the top. And then on the bottom, it's basically 0, but it's positive this time. It's positive really small number. So negative 2 divided by a positive really small number, that's negative infinity. So notice that these are kind of weird because we never really plugged in those numbers. It's like we really plugged in 1, but we just thought about if it was right below 1 or right above 1. But that works out. That's what you have to do. And you get your positive infinity and negative infinity. I don't know how good of explanation that was, but it is what it is. At least I fixed the mistake. Okay. So these are just pointing out some properties. So these are just some properties we probably should have done beforehand. So this is just pointing out some nice properties about infinity. Maybe should have even done that beforehand, before we did the last example, but we're just going in the order of the book. So notice what they're saying here. So we've got the limit as x approaches 0 of 1 is 1, and then the other one is infinity. So basically they're saying we're doing 1 plus infinity here, and it's pointing out, which we should really already know from Algebra 2, that if you do 1 plus infinity, that's still just infinity. And then what's the next one? They're saying x squared plus 1 is 2, basically. And the cotangent one is negative infinity. So we're doing 2 divided by negative infinity. And so they're pointing out here that if you do a number divided by infinity, that's just going to be 0, like it shows right here. So it might be like a slightly negative 0 if you think about how we did the last example. But negative 0, it's still just 0. So any number divided by infinity is 0. And then the next one, they're showing multiplication. They're showing that the limit as x approaches 0 of 3 is 3. Cotangent is infinity. So if you do 3 times infinity, that's still infinity. That's all these are pointing out. And this should all be kind of intuitive, maybe. If you take some massive number and you add anything to it, it doesn't change it. If you subtract anything from it, it doesn't change it. If you multiply or divide anything by it, it doesn't change it. But if you divide by infinity, you get 0. All right, good stuff. Good stuff. On to the next one. Find the slope of the graph of that. We haven't done power rule yet. Oh, this is chapter 2. So this is just getting into limit derivatives. Okay. Find the slope of the graph. Oh, well, this is just a line. Yeah, Cal going crazy. Cal going crazy for you already? It's still early on in the year. It shouldn't be too crazy yet. You should be getting right about into derivatives is what I'm thinking. Which is actually just about what this is getting into. Chapter 2, that's where the derivatives start here. So how should we explain this? I mean, this is just a line. So what do they want? They want us to find the slope of the graph, f of x equals 2x minus 3, at the point 2, 1. Well, so let's we got to picture it out first. A big thing in calc is you got to think about the graphs. So we don't need to be specific, but roughly what does this graph look like? Well, it's just a line, 2x minus 3. It's got a y-intercept of negative 3 and a slope of 2. It looks roughly like this. So maybe our point 2, 1 is like right here. And so what do they want? They just want the slope of this graph at that point. Well, this is a line. Once we see the graph and once we picture that, the slope of this graph is the same everywhere. What is the slope of this graph? Y equals mx plus b. It's just 2. So we don't even need to do anything because the slope of this graph is just always 2. If it was a curve rather than a straight line, then we'd have to use calc and do the derivative and stuff. But as is, it's just a line. So the slope of the line is just 2. All right, good stuff, good stuff. So here's where we got to use the derivative. Find the slopes of the tangent line of the graph that... Is that supposed to be... That's supposed to be at a specific x value, right? Wow, I got far with the screenshots and I haven't even done any problems. That's kind of embarrassing. At those points. I missed that. That's 0, 1 and the other one. Okay. I'm going to screenshot this as well since I don't think I had the proper screenshot. Yeah, it's math time now. It's not chess. Chess will be later. Chess was also earlier, if you were here for that. It's Mathlab time now. But no one's here for math questions. If you got any math questions, pop them in the chat for sure. But there's nobody here for math questions now. Okay. So, right. So this problem we're going to have to use the derivative for, I think. So what are we doing? Find the slopes of the tangent lines to the graph of f of x equals x squared plus 1 at those points. So first we should picture the graph because it's always very helpful to picture the graph. So let's picture the graph. X squared plus 1. What does x squared plus 1 look like? Well, it's a parabola. More specifically, it's a parabola moved up 1. So that actually helps us for the first one, because at the point 0, 1, well, if it's at the vertex, if it's at the bottom of the parabola, we should really be able to see what that tangent line is, the tangent line is just going to be horizontal because it's at the bottom, right? And so what's the slope of that line? The slope of that line is 0. The slope of the tangent line at 0, 1 is just 0 because it's a horizontal line. Now at the other point, -1, 2, so like roughly that line, that we're going to have to use some calc for. So let's talk about what we're going to have to do there. Because we haven't even talked about the derivative yet. So how does this go? So I guess I'm just trying to draw this bigger here. So we have our point right here. We'll call that our -1, 2. And then what are we going to do here to try to find the slope of that tangent line? Because we can't just calculate a slope of one point, right? That's the whole thing about the derivative. So what we're going to do is we're going to imagine this other point. Let's call that point just some x value. We'll call it a. So that's the point a, comma, we'll just say f of a, because notice we're using f of x. So just a, comma, whatever you get when you plug in a for the function. And we can find the slope between those 2 points, right? Like, that slope's easy to find. What's the slope between those 2 points? The slope between those 2 points is y2, so actually the y value first, y2 minus y1, which is actually just 2. So f of a minus 2, y2 minus y1 over x2 minus x1. So like that's our slope. That's the slope between those 2 points. So that's fine. There's nothing wrong with that. But then how do we get calcy with it? How we do it in calc is because we don't want that between the 2 points. We want to see what happens as we drag that point closer to this point. Because see, as we drag it closer, like we get that line, we drag it closer, we get that line, and by the time they're directly on top of each other, we basically just have the tangent line. That's the whole idea here. So what we're going to do is we're going to make that a value, so we're going to take the limit as that a value gets closer and closer and closer to the point that we care about, -1. And that's the idea of the derivative. That's really the whole definition of the derivative. So how can you write that out as like a point or as like an actual equation? What is it? We sort of use different variables, I think, than normally people would use. So I think normally they do the limit as x approaches a, whereas this is f of x minus f of a over x minus a. So that's the same thing that we just did. But anyway, let's just do this out now. So just calculate this. So what is f of a? Well, we know what the f function is. The f function is x squared plus 1. So let's move this over here so we got more room. So we're going to do the limit as a approaches -1 of a squared plus 1, because that's what f of a is, minus 2 over, that ends up to be a plus 1, because minus minus. Okay, that's beautiful, because then what can we do from there? We have the limit as a approaches -1 of a squared minus 1 over a plus 1. And see, this is where your algebra comes in. Because how do you factor a squared minus 1? That should be second nature at this point. That's going to be, so just go ahead and copy this down, a plus 1 times a minus 1. And since that's divided by a plus 1, you see how that just cancels. And so now we have the limit as a approaches -1 of a minus 1. And now we just plug it in. And so it's -2. So the derivative, the slope of the tangent line at that point is -2. That's what we just calculated. So to review again, what was the big idea? Because that's almost the important thing. That's our main point we cared about. This was the other point we were looking at, and we thought about what happened as we dragged that point closer and closer and closer. As you see, when it's there, like that's our tangent line. When it's like we move it closer, if it's here, then that's our tangent line. And as we move those points closer and closer and closer, it got closer and closer to the tangent line. And that's the idea of how you calculate the derivative. Oh, that was a long one. That was a long one. That was deep, though. That was important. That was definitely important. So here we're doing it again. Find the derivative. That's not at a specific point, right? Let's see if they did the same way. No, they did the delta x version, which is the better version. So maybe we'll reimagine that here. Whoops, that's not what I wanted to do. Alright, so we're going to take the derivative of x cubed plus 2x. And we don't know the power rule, any of those yet. We got to use limits. So in the last video, I showed one limit definition of the derivative. Here I'm going to show the other one, which I think is probably the better one. So let's review. What was the other one? The other one, so what was the idea? I'm going to try to say it in words. So the other one, we were taking 2 points. We were taking 2 x values. The one x value was x. The other x value was a. And so we were doing f of x minus f of a over x minus a. So see, that's the slope between the 2 points of x equals x and x equals a. And what we did was we wanted to see as that x value got closer to a, as that x value gets closer to a. So that's not the idea that I usually think about. The idea that I usually think about is instead of thinking about it as 2 different points, you can see what's our diagram. So if we had, this is our point x, and this is our point a, and we're thinking about making them closer together. We're thinking about turning x into a. But the other way to do it is really, it's like the same idea, but it's just so slightly different. It's like we have this x here, and then we have this other point, but instead of thinking them as the points, we think about the distance between them. So in that case, then this x value is x plus whatever distance is between them. So x plus h. And so now it's like we do the exact same thing, but thinking about it as these 2 points. So instead of like f of x and f of a, we're going to have f of x plus h minus f of x over x plus h minus x. And we're going to see here what happens as h. What happens as the 2 points get closer to 0, what happens is that distance between them gets closer to 0. So there we go. That's our other thing. We just can clean it up a little bit. Notice that these x's cancel out. And so that's your good definition of the derivative. And I prefer to use that one. So that's what we're going to do. So let's just straight up use this as a formula and plug in this equation for it. So f of x plus h. So what does that mean? Plug in x plus h for x. So we're going to have x plus h cubed plus 2 x plus h. And then minus f of x. So minus f of x, x cubed plus 2x. And then all of that over h. And again, we're trying to see what happens as the limit as h approaches 0. All right, beautiful stuff. So now we just got to do the algebra. That's all there is to it. This is why we just have to be really good at algebra for calc. So what is x plus h cubed? Well, you should honestly just be able to do it because it's Pascal's triangle, but x cubed plus 3x squared h plus 3xh squared plus h cubed. And then we distribute the 2. So plus 2x plus 2h minus x cubed minus 2x. Distribute the negative. And all of that over h. And of course, the limit as h approaches 0. And so the idea with these limits is everything without an h in it is going to cancel. So we can even just specifically look for that, like this negative x cubed with this positive x cubed, and this negative 2x with this positive 2x. Because now the idea is, look how everything has an h in it now. So now, since we're dividing by h, that h will cancel out. Because we couldn't plug in h equals 0 before because we were dividing by h. But now that we cancel out all these h's, it's no problem. So what are we left with? We're left with 3x squared plus 3xh plus h squared plus 2. So we don't even have a fraction anymore. And remember what we were doing? We were doing the limit as h approaches 0. And now there's no problem. Now we can just plug in h equals 0. So what do we get when we do that? The 3x squared just stays the 3x squared. The next one turns to 0 because you're multiplying by h. H squared is also 0. And so you're just left with the plus 2. And that should be the derivative of this function. If you know the power rule, you can check your answer real quick. Does that make sense? And if you know the power rule, you will see that it does. Okay. Well, that was fun. That was fun. Am I on the wrong Zoom? Honestly, I think I am. Maybe. I don't know if this is where I was before or not. Yeah, no chess for now. It's math time right now. But you can definitely still hang out. Math is good. Alright, so find the f prime of that, then find the slopes of that. Okay. Okay. So what do they want? They want the derivative of f. Okay, well we can do that. F of x is the square root of x. So let's remember, what is the main derivative formula we're going to use? We're going to use the limit as h approaches 0 of f of x plus h minus f of x over h. And so now to do the derivative, we've just got to plug everything into that. So what does that give us? That gets us the limit as h approaches 0 of f of x plus h. F of x is root x, so root x plus h minus root x over h. And now we just got to simplify. Again, that's the hard part. So what do we actually have to do here? Well, the square roots give you the hint that we're going to have to do the rationalizing technique, where we multiply the top and bottom by that. Because now let's see what happens. Well, it's a difference of 2 squares, so the middle terms cancel out. We're just left with x plus h minus x on the top, which is gorgeous. And then on the bottom, we have the h, but don't forget we also have all of this. But we don't want to distribute it, because look what happens. These negative x's cancel on the top, which means we can just cancel out these h's. So all we have now is the limit as h approaches 0 of 1, because everything canceled out on top, of root x plus h plus root x. And now it's super cool because now we can just plug in h equals 0. When we plug in h equals 0, we get 1 over root x plus root x. And so what is that? 1 over 2 root x. Beautiful stuff. Beautiful stuff. Oh, we didn't finish though. How you enter the equation from the PDF to the note? I just copy it. So I go, you can just straight up do that and then copy it. And then you come back over here and you paste it. That's how it's done. Man, I stopped recording before I finished this video. That sucks. I guess I'll just have to splice two of them together. That won't be that big a deal. Or maybe I'll just do them as two separate videos. That'll be fun. Part 1, part 2. Alright, part 2 to the last example. Because we didn't find the derivative at the specific points, or discuss the behavior at f at 0, 0. So let's go ahead and do that. Find the slopes of the graph at f. So we already found the derivative in the last video. So now we just need to plug in x equals 1 and x equals 4. So you plug in x equals 1, what do you get? Well, you just get 1/2. So that's the slope at the point 1, 1. What if you plug in 4, 2? Well, if you plug in 4, because it's just the x value, is all that matters. X equals 4. 1 over 2 times root 4. Well, root 4 is 2. So 1 over 2 times 2 is just 1 over 4. So the slope there is 1 over 4. And so that's why I skipped it, because it's just so easy. Now we just got to plug in the x values. And then lastly, discuss the behavior of f at 0, 0. I mean, I don't think we need to talk about derivatives for that. Well, 1, we could see what is the derivative at x equals 0. If you plug in x equals 0 here, you get 1 divided by 0. So that shows us right there that the derivative is undefined. But why is the derivative really undefined primarily? Is because the graph ends there. That's what root x looks like. So the graph ends at 0. And so if the graph doesn't have something on both sides, it can't have a derivative, I don't think. And so I'd say primarily that's why it's not differentiable at 0, 0, because the graph of f just stops there. Okay, that was good. Find the derivative with respect to t. So we're finding another derivative, this time with respect to t. But notice that's just because we're using t as the variable. Normally when we take the derivative, we're taking the derivative with respect to x. But here it's t because our function's on t. So first off, we definitely just want to kind of rewrite the function a little bit and make it look better. Because that's just 2 over t. And then, well, let's just do the same thing. So again, let's write it down. What is the formula for the derivative? The limit as h approaches 0 of f of x plus h minus f of x over h. And then we're just going to plug everything into that and then just do our best to not mess up the algebra. So f of x plus h, 2 over x plus h, minus f of x. So just, I'm going to go ahead and do it in terms of x. Just know that we're doing x. It's supposed to be t, but the variable you use doesn't really matter. So 2 over x plus h minus 2 over x over h. And so again, it's the limit. So it's just one of these classic limits. We just got to simplify. And then once we simplify, we'll be able to plug in 0. So what can we do to simplify? Well, you got the fractions. I mean, anytime there's two fractions added or subtracted together, I'm like, well, we can't do any nice things to divide them because it's two things added or subtracted together. But if we combine those into one fraction, then we can do some good stuff with it, because then we can actually like divide it by h meaningfully. So I would combine these into one fraction. So how do I do that? I mean, it's just a pattern of common denominator. So I'm going to do that times that, 2x, minus that times that, minus 2x plus h, over that times that. So that's just finding a common denominator. But it kind of blows a lot of people's minds a lot of the time when they see that, of how easy it can be to think about. And see, this is nice because now it's just a fraction divided by a fraction. So now we can just keep change flip and go ahead and simplify the top a little bit. So again, shouldn't forget to copy down the limit. Limit as h approaches 0 of 2x minus 2x minus 2h over, I guess maybe I should do that, maybe not. But times 1 over h. Okay. So what happens now? We'll look how these two x's go away. Just like a lot of happens. Without the h's are all gone. So now we can cancel out this h. And so what do we have now? Now we have the limit as h approaches 0 of negative 2 over x squared plus xh. And see how now there's no problem plugging in h equals 0. Now we just plug in h equals 0. We get negative 2 over x squared. And then let's go back up and let's think about, does that make sense based on the power rule? If you know the power rule, and it does. So we're good. Okay. When's the checks back on? Later tonight for sure. Probably around 9:30 maybe. But this is the one schedule I could maybe try to keep because we got Mathlab at 8. And like I'm so used to having Mathlab at 8. Like I'm not going to miss Mathlab at 8. And then if there's nobody in Mathlab, we could always do this. And if not, I need to do a few of these every day. I mean, I need to do at least 2 every day. I really should be doing 4 every day. 4 of these problems every day. Because I'm trying to post these on my YouTube. Yeah, if you want to go check out my YouTube, mathlab.online/YouTube, then that's what I'm making these videos for. That's where these are going to go. But I want to do 2 a day. I mean, ideally, I want to do 4 a day because I want to do 2 Algebra 2s and 2 Calculus 1s. But that's just been a lot. I need to get ahead and then start doing that. I mean, I should be able to do 4 problems a day. It's not like they take that long, as you see. How many have we done here? 1, 2, 3, 4, 5, 6, 7. So we've done 7 so far, and it's only taken 40 minutes. So I should be able to do 4 a day. That's kind of why I'm trying to get ahead. And that's why I'm only posting 2 per day for right now. Anyway, what are we doing here? The function f of x is x minus 2, shown in, I don't have the figure. It's continuous at x equals 2. However, the one-sided limits are not equal, so it's not differentiable. I mean, I can just graph this. I don't need to have... I know what the graph of this looks like. It's there, there. X minus 2, so it's 2 to the left. I can't do that, can I? No. But I can do that and that. So that's our graph. Yeah, okay, that makes sense. So this is another example that's not really a problem. It's just kind of telling us something. But let's look at what it has to tell us. So we're talking about this function, f of x equals the absolute value of x minus 2. So you see I sketched it for you there. And then they're talking about the one-sided limits. So they're like right here at 2. They want you to notice that the derivative on the left side. What's the derivative on the left side of 2? Of this line right here. We'll see how it's just a line. And if you know absolute value, that should be negative 1. That's what that tells us right there. You see, they actually calculated it, but you can just look at it. It's a line. That slope is negative 1. But then what happens at 2? At 2, it turns around. And look at that slope over here, 1. And so what they're getting at here is that since there's not a smooth change, there's no derivative here at the corner. So at x equals 2, there is no derivative. And honestly, the best way that I have to show that, I used to do this on the edge of my desks at school all the time, but the NumWorks calculator works for it really well too. Because the idea is, let's see how well this is going to look. If you get right here, notice that when you tilt, say the pencil is the tangent line and the calculator is the graph, notice that when you change the slope of the tangent line, the point of contact changes too. In other words, to say at any single point of contact, there's only one slope of the tangent line. And if you change the slope of the tangent line, you go to a different point of contact. And so that's differentiable. At every point, there's only one derivative. That's versus these sharp corners here. If we're right on this sharp corner, then now see how if we change the slope of the tangent line, it actually just stays at the same point. It doesn't move. The point of contact can remain the same and still have different slopes. And so that's why there's no derivative, because there's no singular output. You can have as many slopes as you want here on this tight corner. And that's exactly what's happening with this graph. You can draw a tangent line like there. And see, it's still sort of tangent. Is what it's tangent. Tangent's just like crossing through one point. So it's like you can draw a line here that crosses through one point. Or crosses, all these lines are crossing through like the same point. They just all have different slopes. And so that means it's not differentiable because there's not a singular slope. And see how that's different than if there was a curve. And we talked about like this point right here. There's only one tangent line. You can't draw another line that goes through that point that's tangent, that goes through that singular point, because it's a curved. But on a pointed surface, you can. So the gist of this example is that it's not differentiable if there's what you call a cusp. A cusp just means a sharp corner. So if there's a sharp corner on the graph, it's not differentiable there. That's all that's saying. All right, good stuff, good stuff. Should we just keep going? This is another one of those. The function is continuous at x equals 0. However, because the limit equals infinity. Again, I didn't get the finishing part of that. Is infinite, you conclude that the tangent line is vertical, so it's not differentiable. I don't like that conclusion, frankly. If it's got a vertical tangent line, I don't like the conclusion that it's not differentiable. But that is correct, technically. All right, another problem that's just telling us something. So we got the function f of x equals x to the 1/3. So that's the cube root of x. We have the graph. It's going to look like this. This is the inverse of x cubed. So, however, because the limit, and they see we calculated there, equals infinity, which we can also just draw, maybe your Algebra 2 teacher hopefully pointed that out, is that this is totally vertical in the middle there. It's got a vertical tangent line. So what is the slope of a vertical line? Well, it's infinity, honestly, because it goes up really fast. Or you might have said undefined. And so I don't really like this answer, I guess. I mean, it makes sense. But so what is the slope of this line? The slope of this line is undefined. So can you take the derivative here? No, you can't, because it's not defined. Because the answer you get is the slope, but the slope is not defined. So because you get infinity here, because the slope of this tangent line is infinity or undefined, it's not differentiable there. And I think that's a little weird, but that's how the cookie crumbles. That's the what's the word? That's the convention in math. I mean, I'd call it convention. That's just what we say. If the tangent line is vertical, if the tangent line is vertical, you can't take the derivative. But see, that's why it's weird, because if the tangent line is horizontal, you can take the derivative just fine. It's 0. So if you get a tangent line of horizontal, that's no problem. But if you get a tangent line that's vertical, we say we can't get a derivative, which makes it sound like we can't get a tangent line. But we can. That's why I don't like the wording for that. All right, cool. I need to sneeze. Oh, that was huge. That was huge. Oh my gosh. Okay. Wow, we're on to the new section. So is this where they start talking about power rule and stuff? Yeah, definitely. Let's confirm that, though. Graph with a sharp turn, graph with a vertical tangent, yada yada. Yeah. And then this section, basic differentiable rules. Right, so the derivative of a constant, and then the power rule. All right, cool. Should we prove the power rule? Man, I'm not even sure like how to prove the power rule exactly. So what do we have? If we have the derivative of x to the n, that's f of x. Here, I'm going to record this. Well, let me do this one first then. All right, getting into section 2. This isn't a good, fun section because now we get to stop using those limit rules all the time to take the derivative. We get to learn some of the shortcuts. So here's the first shortcut. If we have an equation like this, y equals 7. I mean, first off, you can get it right from the graph. What does the graph of that look like? Y equals 7. So if there's our plot, y equals 7 is just a horizontal line, right? It's just everywhere where the y coordinate is 7. And well, what's the slope of that line? The slope of that line is 0. It's a horizontal line. So the gist of that then is if you take the derivative of a constant, of a number, it's just 0 because all of these are just horizontal lines at whatever the constant is equal to. Even this one down here, see, it's like an expression, but it's all just a constant. And if you take the derivative of a constant, it's 0. That's what this example is trying to get across. Okay, now we got the tough stuff. All right, now we got the good rule, the power rule. So before we use the power rule, we need to derive the power rule. And I'm not sure I've ever done that. So let's try to do it right now for the first time. So what is the power rule used for? It's used... Wait, hang on. Let me add a new piece of paper here. Okay, so it's used for functions where we have x to some power. So let's do here x to the n. N can actually be any integer. Or at least it should be. It can be. So let's write that. N, not any integer. N is any real number. That's what I meant. N can be any real number. Except 0. But it works for any other one except for 0. Okay. So what can we do then? What is the limit definition of the derivative? The limit as h approaches 0 of f of x plus h minus f of x over h. Okay. So I see how this works if it's an integer. I don't see how this is going to necessarily prove it for other stuff. But let's see. So we have x plus h to the n minus x to the n over h. And make sure that looks like an h and not an n. Okay. So how does this work out? I mean, what they do is Pascal's triangle. But Pascal's triangle ideas assume integers. So I guess we'll at least for now show it that if n is an integer, it works. And then we'll look at what they did. So, what can we do now? Let's copy down our limit. Limit as h approaches 0. So we can use Pascal triangles ideas where we foil this out. It's going to be x to the n plus some number. I'm just going to call it like a naught times x to the n minus 1. Actually, we know what this number is, right? Because in Pascal's triangle, like you think when it's when it's cubed, that first number is 3. Like we know the first number. The first number is actually just whatever power that was. So that's just going to be an n. And then the other numbers, I think we're not really sure what they are. So that'll just be like different a values. Oh, but then, shoot, this has to have an h on it. This has to have an h on it. Is that's h to the 1, and then the next one is x to the n minus 2, h to the 2, and then the next one is like some other number that we don't know, but then x to the n minus 3, h to the 3, and then like dot dot dot, all the way down to h to the n. Alright, so see how that's just like Pascal triangle ideas? Just like to infinity, because we don't know what n is. But then, minus x to the n over h. And then let's actually get this back off the wall because we're doing the limit as h approaches 0. Alright, so what can we do now? Now we're in the simplifying stage. So let's cross out our x to the n's. And then look how now everything has an h in it. So we can cancel out this h with everything on the top that has an h in it. So all of these h powers decrease by 1. But then what happens next? We're plugging in h equals 0. So when we plug in h equals 0, we get all of these things that still have an h in it, like that one and all of these over here. They're just going to go away because if h equals 0, they're just going to turn into 0. And see, all we have left is the thing that didn't have an h in it, the n times x to the n minus 1. And so that shows us that if that is our function, the derivative is what we just had down there, n times x to the n minus 1. And that is the power rule. I suppose we just showed it when n is integers, but it should work for everything as well. So that's a nice little proof. Let's see if that kind of agrees with what they did. See, they did see if n is a positive integer as well. So this proves the case where n is a positive integer greater than 1. Oh, yeah. You will prove the case for n equals 1. Yeah, that's just a constant rule. All right, so they just actually leave it there. They don't talk about that yet. All right, so we're on the same page as them. I guess we'll prove that when we need it. But there's the power rule, nicely written out how they like to write it out. All right, that was a long one too. All right, should we do one more and call it a night? I think that makes sense. Well, then we could switch to chess. After a quick break, maybe. Now I'm curious, how do you prove the power rule for non-integers? Do they not? Oh, in exercise 76, section 2.5, you are asked to prove the case where n is rational. Okay. Does it not work if it's irrational? It should, right? Oh my gosh, we never even did the problems. We never even did these problems. So now that we've found the power rule, now that we know what the power rule is, quick refresher, it's right here. Notice what we were even doing. You're taking this power, you're moving it to the front, and then you're subtracting 1 from the power. You're decreasing the power by 1. So now that we know it, let's apply it. So the first one, x cubed. Well, what did we just say? To get the derivative, we're going to bring that power to the front and then decrease the power by 1. So the derivative is 3x squared. And that's so much nicer than having to use the limit definition to find it. We can do the same with the other ones, but the other ones, they're pointing out that we just need to rewrite it first. And I know we didn't show this, but maybe we'll have to come back and prove it later. But the power rule works for any exponent. I really think any real number exponent it works for. So we're going to do the exact same thing. We're going to be taking the derivative. So we're going to move that power to the front, move the 1/3 to the front, and then decrease the power by 1. So I'll go ahead and write it out for now. 1/3 minus 1. And then we just want to simplify. And I think it's nice when we simplify to write it in the way it looks like before. So I'd say let's get rid of the negative exponents. Let's put that to the bottom. So let's make it 1/3. And then let's make it a cube root too. So it's to the 3rd. So it's the cube root. But then now it's of x squared because of that 2 up there. And yeah, that's what we got. And then the last one, again, we need to rewrite it. So this is a negative exponent already. This is x to the -2. So how are we going to use the power rule? The same exact way. we're going to bring that power to the front. We're going to bring the -2 to the front. And we're going to decrease the power by 1. -2 minus 1 is -3. And then again, I'd just like to rewrite it. So negative exponent, so let's make it a fraction, -2 over x cubed. And that is the derivative. Those would have taken us so much longer if we had to use the limit definition. But using the power rule, it's pretty simple and pretty quick. All right, that was some good stuff. And you know what, y'all? It is 9 o'clock. That means it is time for Mathlab to be over. So I hope you all enjoyed. We'll be back tomorrow. Definitely pop in if you got any math questions. I think I was on the wrong Zoom at the beginning, so unfortunately some people might have come and I just missed them. But it's all good. We'll be back for chess later, so keep on the lookout for that. And I appreciate y'all. See you later on TikTok to start. And on YouTube.